This YouTube video covers my note set for Motion for physical science at MSU, Texas. Today we're going to talk about velocity and acceleration. We've seen this slide before. We used it when we talked about vectors and scalars. And it's important to recall that we were going to use speed as the scalar quantity. We just need a magnitude. And velocity as the vector quantity. Requires a magnitude and a direction. Again, we'll kind of use them interchangeably because what we really want to know is how far we went in a given amount of time. And we, of course, can manipulate the equation around so that we understand each of the elements when they're needed. For example, if we know the displacement and elapsed time, the original format of the equation works fine. We can manipulate through algebra to get distance or time if those are missing variables. Here we have a v with a bar over it, and we'll explain that a little bit more, but we mean average speed when we put the bar on top. Let's consider first the idea of constant speed. In other words, the object of interest is moving the same amount of distance over an equal amount of time intervals. This car, shown here, is covering 3 kilometers total distance in a total of 180 seconds. We can break it down into the individual kilometer intervals, 1 kilometer per each interval. And we find that at each interval, we have traveled 60 seconds. This means that we're having a constant speed of 1 kilometer per second, which you also know as 1 kilometer per minute. Let's take this out for a trial run. Here's an example question. Imagine you're in Canada driving a car that's made in the United States. The road signs indicating the distances to the various destinations are given in kilometers, of course, but your speedometer only reads in miles per hour. If you're driving 60 miles per hour, how much time will it take you to get to a city that is 200 kilometers distant? First, we need to realize what the question is asking and what's being given. The question is how much time will it take? That is a question of time. Our original relationship for velocity is that v is equal to distance over time. So we'll solve for time by doing some mathemagic, some algebra, basically by moving things around, multiplying each side by t over v. What this does is places t on the left-hand side, and we end up with d over v on the right-hand side. Terrific. But let's look at what's given here. We're given 60 miles per hour and 200 kilometers. Do you see the discrepancy here? Miles per hour, kilometers. Those are not the same units. We will need to make a conversion. You can convert from 200 kilometers into miles or 60 miles per hour into kilometers per hour. Either way is fine. I'll give you an example here where we convert 200 kilometers into 124 miles. Simply what we're doing is multiplying by the conversion factor that there are 0.621 miles in every kilometer. That being the case, the kilometers cancel out, and we're left with 124 miles total distance. We return to our t equals d over v expression now, as the units are all correct. 124 miles divided by 60 miles per hour leaves us with 2.1 hours when it's all said and done. The miles cancel out, and hours are left in the denominator of the denominator, meaning that they are in the numerator, and that we have hours as our final unit. I must stress again, write the units each time you encounter a problem. The units are super important, and that's really what science is about. Of course, you can convert this out of hours into hours and minutes. If you do so, you come up with 2 hours and 6 minutes. I want to talk about the idea of average speed or average velocity when we consider a direction. Average speed allows us to talk about what happened over the total amount of observations and works when we have constant speed or if we have a change in speed. Let's look at constant speed again. In this case, we have an automobile that is traveling from the 50-kilometer mark through the 100-kilometer mark to 150 kilometers away. That's a total transit of 100 kilometers. 150 kilometers minus 50 kilometers is 100. In order to do this, the elapsed time that it takes is 1 hour to get to the 100-kilometer mark and 2 hours to get to the 150-kilometer mark. So again, what we're looking at here is constant speed. The average speed can be found by looking at the total displacement, which is 100 kilometers, divided by the total change in time, which is the difference between 3 hours and 1 hour, meaning that we traveled 2 hours. That leaves us with a total of 50 kilometers per hour. I want to make a graphical representation of this, and I think you'll find it handy to do so when you're thinking about these problems. So here's our Cartesian graph, and on the x-axis, the bottom, we have time in hours. And then on the y-axis, going upwards, we have the amount of displacement, or length changes, in kilometers. Remember, we're starting at 1 hour time at the 50-kilometer mark. So we place a dash right at the beginning. The average speed in this problem is 50 kilometers per hour. I would like to look at this graphically. I think there's power in doing so, and I encourage you to look at a lot of our data graphically. The Cartesian graph is very useful for understanding what's going on. So here's my graph paper, and on the bottom I put time in hours. Time makes sense on the x-axis because it is the ultimate independent variable. None of us can control it. We'll put the other variable, displacement or change in length, on the y-axis. And then we'll record our observations as seen in this problem. Here's our first observation. We noted that at the 50-kilometer mile marker, we are at the first hour. At the 100-kilometer mile marker, we're at the second hour. And at the 150-kilometer marker, we're at 3 hours. I've added a fourth observation here, but this is at constant speed. The results should be the same, although our numbers will slightly change in our relationship. What was our relationship again? Well, average velocity is the total amount of displacement over the total amount of time that we consider over this interval. Well, now we have 3 hours to consider and 150 kilometers traveled, but it yields the same answer as the previous slide, 50 kilometers per hour. If you are at constant speed, then your incremental velocity, v without the bar over it, is the same as your average velocity. Let's look at an increment here. I've outlined it with a couple of lines. A line indicating the change in displacement, or rise on the graph, is a total change of 50 kilometers. Our change in time on the x-axis is an hour, marked with the blue line here. Our relationship then becomes 50 kilometers per hour for this increment, and that's 50 kilometers per hour once again. You can do it for any of the increments in here. I do want to call to your attention that we don't have a direction, so technically this is speed and not velocity, but it would be confusing to use s as a variable, as we're going to use it for time as well, so I will avoid doing it at this juncture. Now I want to consider what happens if speed changes during part of our observations. I've got a slightly different graph here to look at this, and we'll note the changes from the previous graph. So let's go to our observations. Our observation at 1 hour is still the same. It's 50 kilometers. However, at the 2 hour mark, it's different from our original observation. Our original observation is right here on the fainter line. After 2 hours on our original constant speed graph, we would have been at 100 kilometers. But now we're right here. Careful measurement on my graph indicates that this is 75 kilometers. However, if we move along to hour 3, we're at 150, and our faint pink line joins our new data, indicating that this was the same as the previous problem. And then finally, our last observation at 4 hours happens at 200 kilometers. Now, the important thing to see here is that there is a difference from our original data, but in terms of average velocity, it's not going to matter. Why? Because our total displacement is still 200 kilometers minus 50 kilometers, or 150 kilometers. And our total change in time is 4 hours minus 1 hour, or 3 hours. That gives us a final answer of an average velocity of 50 kilometers per hour. What's changed is incremental velocities or speeds are different depending on where you look. The one place we can see this is right here, where I've graphed it out. Notice that our displacement on this, or our rise on the graph, is 75 kilometers. That is 150 minus 75. Our change in time is 1 hour. That indicates that over this line length right here, our speed was 75 kilometers per hour, and that's different from the average. Another way to get the average velocity is to sum up all your observations and divide them by the number of observations. If we looked at all our increments, including this one here, we'd see that the first one is 25 kilometers per hour. The second one, which we calculated, is 75 kilometers per hour. And then the last leg of this trip is 50 kilometers per hour. Adding these together gives us a total of 150 kilometers per hour. There are 3 observations. We'll divide by that, and we still end up with 50 kilometers per hour.